Now, see here what is satellite. You know, satellite is a body which revolves around the planets. Like you can take moon revolves around the earth, so moon is considered a natural satellite of the earth. There are many artificial satellites these days which has been launched, and these satellites are revolving around the earth, and these satellites are used for different purposes, like for communication purposes and also for weather monitoring and all other etc. So, we have to now understand about the orbital speed, time period and height of the satellites. So, see here, suppose there is a earth and this is the radius of earth and mass is m. Now, from the center of earth at a distance r, suppose there is a body of mass m, we can consider a satellite is revolving like this. When this satellite is revolving here, so here r is equal to r plus h, this is height h from the surface of earth and this is mass m. So, see here, one centripetal force is acting on this body of mass m, that is F c is equal to, we can write mv square upon r. So, v is the speed of the satellite with which it is revolving, and this v is known as here orbital speed, and r is known as here radius of orbit. Now, at the same time, when the body is here, it is experiencing gravitational force, and gravitational force F can be written, F is equal to gm m upon r square. So, in equilibrium, this gravitational force provides necessary centripetal force. So, now we will derive formula for the orbital speed. So, we can write here, just now here I will remove this diagram and use these mathematical equations. So, we can write here mv square upon r is equal to gm m upon r square. This and this will cancel, this and this will get cancelled. You will be getting v is equal to under root of gm upon r, that can be written gm upon r plus h. R is the radius of earth, h is the height above the surface of earth. So, this is the formula for orbital velocity. Now, see here, the orbital velocity is independent of the mass of the satellite because it has been here cancelled now. It depends on the mass of the earth and it depends on also the radius of its orbit. If the larger orbit has the larger radius, orbital velocity will decrease. Now, we can go further here. We have already done g is equal to gm upon r square. So, we can write gm is equal to gr square. So, we will be getting orbital speed under root of gr square upon here r plus h. So, we can write this formula also for this in place of the gm. So, this is about orbital speed. Now, after orbital speed, we can calculate formula for the time period of satellite. You know, the time taken by the satellite to complete one revolution is known as its time period. So, we can write here t is equal to 2 pi r upon v, r is the radius of circular orbit and v is the speed, orbital speed. So, total distance upon velocity is equal to time, that is the time period. So, we can write here 2 pi r upon, here we can write under root of gm upon r. Now, if we square both the sides, we will be getting t square is equal to 4 pi square r cube upon gm. So, this is the formula for time period, but now see here this portion, this quantity is constant. So, we can write t square is proportional to r cube. It means square of the time period is directly proportional to cube of the radius, and already we have done in the starting of this chapter, that is the Kepler's law, that was here the law of periods. So, law of periods already we have done. So, now we can also get the expression for the height of the satellite. So, now we have derived formula for the time period. So, we can calculate the expression for height also. So, we can write r cube is equal to gmt square upon 4 pi square, and we can write r is equal to gmt square upon 4 pi square raised to power here 1 by 3, and this r can be written r plus h is equal to gmt square upon 4 pi square raised to power 1 by 3. So, h is equal to gmt square upon 4 pi square raised to power 1 upon 3 minus r. So, this is the expression for the height of the satellite from the surface of the earth.